Okay, slowly we are looking into the probability function, probability density function, probability distribution functions, and the personality of a probability function, like characteristics of probability function. And this is I'm going to cover today slowly getting into the probability model. And of course, first model is going to be the Gaussian probability model. Sometimes I call as a Gaussian probability function, or the normal probability function. It's all the same thing, right? And that's a very special function. And last week I mentioned to you, I really assigned a little homework problem saying that search for in your area of thesis research, get that model probability, the Gaussian probability density function, which you could find easily in your area. Then I'll select something like a 2 or 3. Then you can present, we can learn where such a model can be applied. And starting this week and early next week, I'm going to introduce other types of probability model. We are all 12 now? Oh, it's successful. Oh my gosh. Thank you very much for coming, It's great. So starting with the 12, still 12. I told you I'll do my best, and of course you will do your best. And rather than tedious class, I like to have really the vital and the healthy class. As Yoon-suk and Jungan mentioned, if you have to go away, during the class hour, you can go away every week. You can, period. So attending the conferences, some special meeting away from here in campus, let me know, rather than just to skip the class without letting anybody. So that's okay, all right? So next week is planning a little bit, like a log normal distribution, very powerful distribution. Again, if I say probability distribution function, of course you can point to specific cumulative distribution function, but in general, probability function, probability density function, distribution function, you know what exactly that means. So you can treat as a probability functions, okay? Then of course, for structure reliability computation, you have to bring back the model. Then we have to use it. Develop the model is a clue for your work, for your own area. So you can't simply assume, too risky. So you have to develop based on your own knowledge in your area. This is a really graduate school, and learning the probability function is not the issue. But we have to learn, because to set the direction to go, otherwise we don't know where we're heading. So remember, you are taking, whether you like it or not, at least one the statistics course, probability functions, then at least one, two are better than one. Then some of you may say, well, in all the classes I'm taking, they don't use a probability theory. Well, they don't. You said they don't. It's limited. They don't. But if you go up and everything is all fuzzy, everything is quite uncertain, then you need a probability to bring back in. I'm not the expert in the probabilities and statistics, but I know the area where I have to use it, then that's all I do. I'm not the acoustics specialist, but I work in the area of underwater shock wave propagations area. But I just use acoustics theory. I studied acoustics theory, the area, acoustics area that I really need to understand the shock wave, which is a portion of the acoustic wave. Because you can be expert in every area. You can afford to spend the time. You don't have such a time. You don't have such a luxury, but you have to pick up as much as you can to prepare the area that you want to pursue. So that's what the probability model I'm going to talk. Of course, you learn the Gaussian probability function. But I don't want to just learn and just goes away, which I'm insisting you must use it in the area. So that's what I really like to concentrate this semester. After 4 days, right? After 4 days of long holidays, maybe a lot of things may be evaporated because you concentrate on the namchin and yochin, don't you? When I was really in your age, I was very interested in yochin. I had not 3 or 4 at one time, no, just a few in my life. You know, now we have to bring back the stuff we learned, so I'm going to briefly review the few items here. Okay, very simple items. What do you call this? Stupid questions, right? That's a mean, right? Mean of x. The subscript x is a capital letter I usually use to imply the random variable. It can change the value. It's not a fixed value. So e to the x is another name is expected value. So expressing or using the probability density function, this is equal to this is sometimes I use a lowercase, but after for a while you know what I intend to do. Integration limit is from mathematically minus infinity to infinity. In the engineering sense, it doesn't have to be minus infinity to infinity. It never exists. Mathematically, of course, it exists. So in the engineering sense, the lowest value to the highest value. That's what it takes. So minus infinity to infinity. In application, we were dealing with the center of gravity in engineering. Here, out of these 12 students here, some of you are not the really engineering major. So in this class, in other class too, I kept that in mind. Then I'm willing to spend some extra hours for those students who are not. But mostly I cover in class and review in class also. And what's the expression for the mean square value? What's the expression? Mean square value. I use a notation. It's a psi square. It's just a notation. Nothing but just a notation. Okay? What is it? Anybody can tell? E to the what? X squared. Simply x squared. In the integration form, I keep writing the integration form because this course you will love integration. Numerical integrations. So it's x squared fx x dx. If I square it, if I square this guy, what do you call? Jude, what do you call this? Has a name. Who cares? But please care at least this semester until you get your degree. This is a square root of psi square square root. What do you call? Root mean square is called RMS. So this is equal to RMS square. So in the electricity is alternative. The current is alternative. So it's a fluctuating. So they are dealing with the RMS. Okay, it's not the volt square. It's a volt. And the mean square value is the volt square. Mean value is simply volt, linear scale. And another one we learned was psi, I would rather x, psi square, sigma x square. What do you call this? Hey, louder. It's a variance, right? Variance. It's a variance, which is equal to e to the x, capital X, if you want to, mu x squared. And of course, you can express using integration form. And after you expand it, then you have this is equal to psi x squared minus mu x squared. You remember? Remember. I didn't memorize it. As I write a few times, then just stick into it here. And from here, you can say the relation between the mean square value and also the variance is, this is equal to sigma x squared plus mu x squared. The sigma x squared, sigma x is called standard deviation. What that means, standard deviation or variance? As you look at the value, what do you have in your mind? Takashima-san, what do you have in your mind when you hear about the variance or standard deviation? It's a spread, dispersion of the population. Test the data set. If it's a spread widely, is it good? No good. No good. The data set is very fuzzy, so which is not good. For the quality control aspect, if a standard deviation is large, then it's bad. Standard deviation, dispersion about the mean is what the standard deviation or variance is. And the mean square value or RMS value is dispersion, it's a second order, right? Dispersion of the population about the absolute zero, right? This guy. The difference between this and this or this or this or this is the same thing. Linear scale, this is square. This is about the mean equal to 0. This is about the mean. Dispersion. So when you look at the spec, when you buy the material, the spec should tell the standard deviation or variance. Then if it's really high, which is not very good. This is what we learned, okay? Mean is a central tendency where the data set or population locate. So one additional item is COV, coefficient of the variation, which is really, you can say this is a normalized standard deviation. Normalized standard deviation. This COV is equal to sigma x over mean of x. It's just a normalized value. Nothing but just it normalized it. So this is a unitless. So if COV is high, which is not good, normalized, simply normalized. Some people use this guy as delta function. So and the first model, you all know, you are exercising, and you will show us Friday. First model is a normal probability function. probability function, there are two different kinds. One is density function, the other one is distribution function. So normal or Gaussian probability function. First, probability density function. This is simply expression, okay? So this is like a first one they formulate as a probability density function. And I said this is like a bell shape, right? This is, we all know that. It's just a tie with the here. And this is upside down bell shape function. Very useful function. And this goes to infinity, never touches. And this goes to negative infinity, never touches. There is no such a physical phenomena to fit to the Gaussian density function, because it never touches. The tail end never touches, but for engineering sense it's perfectly fine. We can, why? We can accommodate small error. We can live with a small error. That's okay, right? That's what happened. So it's equal to 1 over 2 pi sigma x e to the minus x minus mu x squared and 2 sigma x squared. If I make error, let me know. So question is, do I have to memorize it? No. But if you keep using it, you will end up knowing it. Okay? And as you change sigma x and the mean, then this probability density function maybe can fit into your the data set, whichever that it comes from, whichever it comes from. It could be experimental data set or basic phenomena, whatsoever. If you are not able to find model in your area of research or study, then you can just search for it and understand, then present. And the probability density function. How do you find the probability distribution function or cumulative the probability function? How? You simply integrate, right? You simply integrate, and so fx x, you simply integrate minus infinity to x. This is a specific the value of random the variable. By setting the x, you point that particular point among the range of the random variable. So this is equal to fx x dx. So if you do that, it's going to be minus infinity to x. Then you can 1 square root of 2 pi sigma x e to the minus 2 x minus mu x square sigma x square. If you look at any handbook or our textbook written by 3 authors. First author is Choi. If you look at the Appendix C in that textbook, there is of course a table, like a standard, the normal probability function. You will see the table. So I'm going to show you how it relates and how to use it. But nowadays, if you have a PC, you can just get into the internet. You can get almost everything from there. This is a dx. From this function back to here, if I set mu x is equal to 0, and if I say sigma x is equal to 1, for example, okay, it has special forms. What special form? Mean is equal to 0. This is fx. Mean is equal to 0 right there. And sigma x is equal to 1. So this is a measure of spread or dispersion. So surely the shape is going to be something like upside the bell shape. But mean is equal to always 0. So in this case, of course, if sigma x is getting very small, then it's going to be narrower, and narrower. What does it mean? Accuracy is good. Your data set is good. Your experimental data set, you did really well. If your data set is like this, that's a bad. You were thinking something else when you do the experiment in the lab. Dispersion is no good. Well, some phenomena, physical phenomena, dispersion is higher. That's the fact. Okay. Then in this situation, fx x is equal to 1 over 2 pi e to the minus 1 over 2 x squared. Yeah. This is called the standard form of Gaussian probability density function. This is a standard form. Or it is called the arrow function. Okay, standard form of probability density function. I'm going to show you why. Okay. So I just set this guy equal to 0, that guy is equal to 1. So going back to the probability distribution function or cumulative probability distribution function here, I'm going to set that form over there. I'm going to set z is equal to sigma x minus mu x. Okay. Substitution of the variable. I'm going to set let. This is just the let. Okay, then I'm going to change the integration form. So I'm going to differentiate this guy, dz over the dx. If you do that, that's equal to 1 over sigma x. And so this is dx is here. So this is equal to dx is equal to sigma x times dz. So I'm going to substitute right here. Z is right up there. If I do that, f is equal, I'm going to leave this, the parameter as is equal integration 1 over 2 pi sigma x and e to the minus half z square dx is equal to sigma x times dz. So sigma x cancels up. So if I just rewrite here, this is the integration 2 pi e to the minus 2z square dz. So this is identical form as the standard form, except the z instead of x. So integration limit is minus infinity to z. Z is the right there. Okay. So now I can say this is z. Identical, just change of integration parameters. Okay, then if you two sets of reference book, textbook, Higyu has it, so you may check out anytime, or Jungun has a copy, Yunsuk has a copy. In Appendix C, you will have this sort of the table, or MATLAB CDF. If you look at MATLAB command, you can print out also this one, or any handbook has it. And this is really probability standard form, probability, cumulative probability function. This is the distribution function. Start from 0 to 3.5, and this is a range from 0 to 0.09. And if you look at this, is the shaded area is like a total area. That's what the distribution function is. And the area of half is equal to, what's the half of the area? What's the total area? 1. What's the half? Say half. Half is half, 0.5. half of 1, right? It's a half. Because this is symmetric. It's upside down bell, symmetric, right? Right? So it's area of half of this normal distribution function is half, 0.5. And if you look at here, this is what the limit of the z. This is z value is up to 3.5. Okay, 3.5, but it said the last entry is 0.9999983, which is 1, because half is already in there. So it's covered area up to the 3.59 area here is 0.9995. You follow me, I hope, right? Not clear? Not clear? If it's not clear, tell me, not clear. Or another thing, another answer you could say is, it's clear, but not quite, which is bad. Better not to know. First, to take a look at this, okay? And to define the normal probability density function, and you need 2 parameters only. One is the mean value, another one is standard deviation, isn't it? You don't need anything else. But the probability model, you need more than that. That's what we're going to discuss. There are quite a few different probability functions, but I'll just give you a few, which is quite popular. Then if you need any special probability function, of course you can really study for that model. Not bad, okay? So before I getting into the classical structure reliability model, I'm gonna, by end of next week, I'm gonna really cover the probability model with some application in it. Then you can just grab the physics in your heart, okay, rather than just a number after number, which is not good, okay? And 2 parameters you need in this case. If x1 and x2 are normal probability function, okay? You can prove yourself easy. x1 plus x2 are normal probability functions, okay? You can visualize it. You see, you can visualize. And we're going to cover, when I getting into the joint probability density function, then we can discuss that. And this type of the function, the normal probability function is not good for something like, this is not x, so I'm afraid you would say x. So normal probability function is not appropriate to such as A, for example, to model the ocean wave height, not good. Sea state keep changing. Sea state could be 3, 4, 5, then phenomena, ocean wave height does not follow the normal distribution function. It has, it needs like a skewness. If this is a function, height, fx, and it could come like this. Depend on the wave, it could go like this. Okay, that's not follow. Gust wind does not follow the normal distribution function. No. This is all called, you can fit using log normal distribution. And gust wind is also like this. It's all called the extremal distribution. This kind of the model you can use extremal distribution. I'm going to also introduce extremal distribution. And stock market, when everything is all calm, very nice, happy, every country at dinner time, they bring the wine and drink a wine and have a peacetime. Could be a normal distribution, may fit really well. But the situation in every country like now, it's just up and down and up and down, and stock market just drops to 500 point one day, another day, as the president says a few words, I'm gonna just pump in the $5,000 million in there today, and it jack up and down, could be down next day. That's all extremal distribution functions, okay? And explosion, underwater explosion, which is not the normal distribution function. And nowadays, just before the Chuseok, as you go out to the market, then everything's all jacked up. Price is all jacked up by itself, then come down after the Chuseok. So all the phenomena, we can think of the probability model. But if you say, oh, I don't want to use a probability model, what about just the one spike fixed? Who does that? Government, Treasury Department said, all that the price fixed from today, the vegetable, the petrol should not be more than 1,001. Only Korea does that. No other country does that. Interest rate fixed 3.5. Who does that? Government does that. Free market country never do that. But that's not bad, to really maintain the stability. I think that may be a very good policy for a while. Then they drop. So you remember, I'm telling the fact that depend on the phenomena, you can use a different model. In other words, you must be flexible in your heart. Okay, that's what the reality is. If you fix which is no good. Conservative people, the military people, they are very conservative. That's why they joined the military. So the people who really involved in business, like Samsung chief, 이건희 회장님, he loved, I bet, gambling. I'm not talking about gambling using the card. Maybe he sees it, then he predicts it. Maybe his people conduct the risk analysis and the reliability analysis. Then he could say, okay, here is my 5 jo, which is a $5 billion, all in. And he earned. Sometimes he loses. So here is important property in this case is a skewness. Skewness is, I'm going to talk maybe tomorrow. Skewness is a measure. Measure of the skewness is presented by the third central moment. It's called third central. Why is it central? This is shifted to shift x by the mu x amount, okay? It's a skewness. I'll mention maybe today is Wednesday, Friday morning. I'm going to go through some more central, the third, the central, and fourth central moment. So you have to compute one more parameter. 2 parameters, mean and the standard deviation, are not enough. One more, which is a skewness. But the normal distribution function, you don't need additional parameter. Why? Because it's already symmetric model. Okay, so everything fits really well. And 한수님 교수님 said, time to get out. So we have to get out. So I'll see you on Friday morning. And it's very nice to see you all today. And we'll have a good time. Okay, I want you to speak up. I want you to speak up using English, okay? This is a wonderful chance to use English. And just open up. To learn the English, you have to open up. That's the only way to learn English conversations. Whether it works or not. Do you promise me? Okay. And Friday, I'll spend 10 minutes, 10 to 15 minutes, then you can present your model. Each model may take a few minutes, then maybe 3. Some nice model, which you involve the phenomena in your thesis area. Every one of you have to write thesis work, right? You have to conduct a thesis research, yes, right? So you have to, because you are the only late, you and Takashima, 2 late. You are lucky to have 2 beautiful ladies here, isn't it? Say yes, yes. Maybe you prepare some quick talk for the model. Okay. Don't give a burden. I hate to see you having a burden but just to relax and present. I want you to practice. And some term project you have to give a talk to. No burden. I hate to see people has a burden, just has a free will, just to let it happen. I'll see you Friday.